Right, welcome back. I hope break was nice. Uh, Plan for today is to do more with lenses. Look at the human eye some and more with what happens if you have more than one lens being used at the same time. For the class goings on, unsurprisingly, our last test will be on the last day of class, which will be December 15th. And homework was just due, and I'll post another homework, which will be due Monday, and there will not be a quiz this week. Any questions before we get going?
Could we go over number 3, Professor, from the homework?
Number 3, let's take a look at it.
A lot of angles.
A lot of angles, yes. All right. Oh yeah, that one, yep, lots of angles. All right. So our light is starting going in that direction. 10 degrees above the x-axis, and the first mirror it hits has its normal vector in the x direction. So that is the easier of the two mirrors. So got our mirror. So normal to that. So 10 degrees off normal means it's going to come out 10 degrees off of normal for the first bounce. And the second mirror is a little trickier. So its normal vector is going in the plus x minus y direction, 40 degrees below the x-axis. So our second mirror has its normal vector pointing plus x minus y. Mirror itself going like this. So if we measured the angle between our x-axis and our new normal vector, it would be 40 degrees. But the angle that really matters is the one between normal and our incoming ray, which if we're 40 degrees off normal, then we're going to be 30 degrees off of this. Because this is 10 degrees. So if we come in with an angle of 30 degrees from normal, we are going to leave 30 degrees from normal. So that makes this whole angle be 30 degrees plus 40 degrees for 70 degrees. pretty close to minus y, but still some positive x components. Right. Anything else? Uh, first problem of the day, mostly just review of what we've been over before, looking at a single lens, but applying in a way we haven't looked at before. All right, so just off the bat, only you can prevent forest fires. So just bear that in mind. It's important. So there's a lens, and it's got its focal length, and then very, very far. There is a sun. So light from the sun comes in pretty close to parallel. And is going to meet at the focal point. But it's not exactly parallel because the sun isn't a dot. So you're not going to get an exact point of light here. You actually get an image of the sun. So our magnification equation, or our magnification, is equal to our image distance over our object distance, minus 1 just to take into account the fact that things can be flipped upside down. But for an image of the sun, whether it's right side up or upside down is of not much importance. So how big would the image of the sun be? So if you had a, a very flame resistant screen and you put it right here, how big would the bright dot be from the sun? So yeah, see if you can work that out. And once you have how big that dot is, if you assume that none of the light is reflected off the magnifying glass, then all of the energy that hits it ends up in that little dot. So what would the intensity be in that dot? So see if you can work through it. So for the first question, our image distance over object distance, the -1 times that is going to be our image height over our object height. So the size of our image is going to be the distance of our image times the height of our object divided by distance to the object, or km 50 km times 0.5 meters. So I am uglily mixing units, but that ugliness cancels out. So I just end up with meters. So there will be a bright spot that is 0.00467 meters in diameter. So what would its intensity be? And just remember that intensity is power per unit area. So if all of the light makes it through this lens, which is not quite realistic, there's usually a little reflection off the surface, the power hidden is equal to the power after it goes through. So I mean I1, A1 would be equal to I2, A2, because the powers equal the same. The powers are the same. So I2. So the pi's cancel out, and it's just a ratio of the radius squared. So we would need to divide this by 2 in order to get its radius. And we have 0.04 for the radius of the lens itself. And this will give about 294,000 watts per meter squared. So only you can prevent forest fires. Prevent forest fires. All right. So that is how a magnifying glass can make a fire.
This is like Bond villain level stuff.
Yeah,
Most Bond
I
villains
was
are a little
thinking-
more elaborate.
I was
This
thinking that at the
is-
beginning, like a mirror this big. Just
This is
it's
the 5-year-old that's going to grow up to the Bond villain. This is just a
Yeah.
garden variety magnifying glass. If you really scale it up, yeah, Bond villain.
yeah. I saw the 150 million kilometers and I was like, oh, that's the size of the mirror. That's the radius. That's like huge, incomprehensibly large mirror.
Yes, that would be an Earth's orbit size mirror, which
Oh
would be
yeah.
expensive. Yeah, so this is the intensity here is what you would get on a very sunny day at the bottom of Earth's atmosphere, approximately. And the sun is this far from the Earth and does have a diameter of about that big. So this is just the physics of a little magnifying glass getting something really hot.
So, just a question, why would we not use like a sphere surface area? Why would we use a circle surface area? Because isn't the sun like more like a sphere than a circle?
It is more like a sphere than a circle. The flat sun theory has very few adherents. I am definitely not one of them. But the picture of the sun that you're making an image of, it's kind of a circular picture. So like if you were, taking a picture of it or just looking at how much of the sky it takes up or just the distance between the top and the bottom, you would use the diameter. The fact that the part of the sun that looks like it's in the middle is closer to us doesn't matter that much because they're both so incredibly far away. What matters is just how far apart its top and bottom are.
Okay, that makes sense. So we're just measuring in like across the sun, not up and down, I guess.
Yeah, so the distance between its North Pole and South Pole.
Okay.
Because we're not making an image which will be bulging outwards, and we need to know the bulge. We're making an image on something flat. Yeah, that is, I guess, something I hadn't thought of, that if you were traveling along the surface, yes, the distance would be larger, but what matters is how far apart those 2 points are. So, the radius that I'm using, if you're getting crazy, crazy big numbers, you're probably using one of the crazy, crazy big radii. So I'm comparing the energy at this point to the energy at this point. So for intensity 1, I'm using the 1,000 watts per meter squared. And for radius 1, I'm using 0.04. Yeah, it's how much light hits the lens. If you're capable of getting all of the sunlight into that point, you would be a Bond villain, but we're just getting all of the sunlight that hits this little magnifying glass to get down to that little dot there. Right. So next up, going to look at putting two lenses together. And we're going to start with the hard way and then use it to justify a little trick. So there are two lenses and they are close to each other. There's a lens and a lens. Actually, the second lens should be flatter. I tried. So everything nicely on a line. And for our focal points, our first lens is focal points and our second lens has a 2-meter focal point. So its focal points are going to be farther out. And our object starts out 2 meters ahead of the first lens, which is going to be just outside of the focal point. For our second lens. So to go through the steps on this one, which is not quite drawn to scale, figure out where the image would be after it goes to the first lens. It's going to give you something on the other side, which is not where you usually have objects. So when you try and figure out the object location for the second lens, it's on the wrong side or a negative object distance. And then you can use that to find your final image. So it's just doing this one twice. So see if you can work through that. Start off ignoring the second lens and finding the image, and then use that location as your object, find another image. So this is not an ideal setup for drawing it out. I just don't have a clean enough drawing, but just looking at what it would be if we come in parallel. It's going to go through the focus point. And if we go through the center, it'll just keep going. And if it goes through the focus, it goes out parallel. So if you cheat as much as I cheated, you can see it's going to end up 2 meters behind the first lens or so. And doing the math for it, two meters works. So our image distance doesn't become our object distance. Our image location becomes our object location. So that is our object for our second lens, which if it's 2 meters behind the first lens, this is 2 centimeters, then it's going to be 1.98 meters behind the second lens. So 1 over its 2 meter focal length. It's 1 over our image distance plus 1 over minus 1.98 meters. So we take the inverse of both sides. And it is 0.995 meters. So the final image is going to be about 1 meter from our lenses. Okay with the hard technique, just doing it in 2 steps.
Can you explain why it's negative, the object distance?
Yes, so our light is coming from left to right. So we're looking at an object that is on the right side, not where the light is coming from. The side that an object has no business being on. So our object distances are positive if they're where the light is coming from. And it's on the other side, so it gets a negative distance.
Okay,
Just
but
the
the
sign
image,
convention.
like the DI from the first half, even though it's on the right side, that's positive.
Yeah, so images have the other sign convention. If they're on the side where the light is going to, they're positive. So that if you have the nice happy system where we got our convex lens and an object on this side and an image on this side, then everything is positive.
But then you get a positive image distance at the end, even though it's on the left side.
Yeah, so positive means it's on the side where an image would, so over here. So on the side where the light is going to is positive for images.
Okay, so the image is actually on the right side at the end of all of it.
Yeah, both of the
Oh.
images are on the right side, yes.
Okay.
Yeah, it's not the only way a sign convention could have been set up, but just sticking with this one consistently gives right answers. And it should be smaller than that. It should be short. That's where the last one's going to be. All right. So the easier way to get this almost right and close enough for many applications. Two lenses close together. Light's going to bend once through the first lens and then bend again through the second lens. Which we treat the bending of the front of the lens and the back of the lens if it's all just happening in one spot. We can do that again, where we can treat all the bending of the first lens and all the bending of the second lens if it's just happening together. When really it bends a little as it enters the first one, exit the first one, enters the second one, exit the second one. But if things are thin enough and close enough, such that the thickness of the lens is much less than their focal lengths, and the distances between the lenses is also much less than their focal lengths, just putting it all together, it's nice. And that works with the focal length of two lenses together is not the sum of the focal lengths, but the inverse of two lenses together, or three lenses if you got a bunch of lenses close, or four lenses, or you can keep going if you want. So it's the inverse of the sum of the inverses. Another way of looking at this is that the power of a lens, where I'm not using power in the sense of watts, but power is in focusing power, is equal to the sum of the focusing power of the lenses that go into it. So this would be measured in diopters. So you can just add up the inverses to get the power of the resultant lens. So using that technique on this problem, so our new focal length is going to be 1/1 meter plus 1/2 meters. Got 2/3 of a meter. And we can just use this once. Just gonna give so 3/2 minus 1/2 is 1. So the fact that there is a little gap here means we're getting the distance of 1 meter instead of 0.995 meters behind the second lens, which is, it's all really, really close. Ooh. If you have a quantity of inverse meters, is it called diopters? Oh, singular or plural? I think you can put an S on it for, yeah. So you can say so-and-so diopters. Yes. So if you've got something with a focal length of 1/2 meter, it would be 2 diopters. So part of the reason why the diopter or inverse meter is used as the measure for lenses is that you can combine the inverses of their focal length just by adding them up. But you can't combine the focal lengths just by adding them up. So it's a measure of how much bending. The greater the number of diopters, the less distance it requires to focus in light, so the stronger it is at bending light.
So wouldn't we kind of want to get the distance between the object and like the center of the two mirrors? Like I was kind of thinking it might be like 2.01 meters. Or
Yeah,
does that not matter?
that would be better. Yes, if you wanted to do, picking some spot in between them would be better than just picking one or the other. I agree. The justification for not doing that is not the best, because picking a spot between them is better. But if the distance between them is big enough that it matters a lot, the assumptions that go into making this just don't work at all anyway. But if it matters a little, yeah, you would probably minimize that by taking a spot between them instead of picking one or the other. I agree.
Okay, that makes sense. This only works if they're close together anyways,
Yes.
right? Okay.
But you can get less error by not taking one or the other one, but some spot in between. If you want to be super careful, you might weight it based on how strong the lenses are, being closer to the stronger one and farther from the weaker one. All right. A cool thing about this technique is it allows to measure diverging lenses. So practically speaking, it can be pretty easy to measure the focal length of a converging lens. If you just hold it up to a faraway light, sunlight, it's just how far above the ground you need to be to make the little dot. That's the focal length, assuming your sun's directly overhead. So just what's the distance it needs to focus parallel incoming rays. But a diverging lens doesn't do that. So a technique for measuring diverging lenses is pairing them with a stronger converging lens. So if we have our converging lens, then our incoming rays are going to focus 25 centimeters behind it. If there is a diverging lens, incoming parallel rays, they don't focus, they spread out. But if we pair them up and put them very, very close to each other, and the focusing power of our converging lens is greater than the negative power of our diverging lens, it's really, really close, acting kind of like one lens. It's parallel rays. Will meet. So see if you can figure out the focal length of the diverging lens. Using this technique. So 1 over our combined focal length. Is equal to 1 over the focal length of our first lens plus 1 over the focal length of our second lens. So 1 over 0.8 meters. Now you could work in centimeters for this. 0.25 meters. So 1 over our focal length of the second lens is the power of the second lens, or minus 2.75 inverse meters or diopters. And the focal length is minus 0.3636 meters. Good on this one. Cool. And going back to Bradley's question, so you would say a 3 diopter lens, but you could also say, a power of 20 diopters, which I guess is not the most straightforward answer, but it's what's said. No, F2 is going to be negative in this case because the one, it's diverging, so that's going to make it negative just from its setup. But if we look at the left side of this equation, we have 1 over 0.8, and we're minusing 1 over 0.25. So the negative quantity is greater, 4 inverse meters compared to 1.25 meters, inverse meters. So we end up with something negative on the left side. So our right side of the equation needs to be negative as well. Okay. Yeah, F2 is, in this example, the focal length of the diverging lens. That lens. 2, 1. The bottom is combined. Let's get to the physics of your eye, which is not really much beyond the physics we've already been doing in broad strokes. Your eye has a lens. It works with lens physics. The actual detection of light, a little more complicated, pretty cool. But just looking at the eye as a system for focusing light. Got your eye. There's a lens in it. And parallel light, if you have good far distance vision, parallel rays meet at the back of your eye. So this is an oversimplification because most of the focusing of light doesn't actually happen at the lens of your eye. it happens as it enters your eye, because it's the difference in index of refraction that gives bending, and the difference of index of refraction is much bigger going from eye to inside your eye. So passing passing through at your cornea, than it does going from the inside of your eye to the inside of the lens of your eye and back to the rest of the inside of your eye. Because the indices, the index of refraction of their lens is a bit higher than its surroundings, but not a lot higher. So most of the bending happens at the front surface, but still some happens on the lens. If you want to look at something which is closer, the image distance is going to be the same. The distance between the front of your eye and the back of your eye isn't changing. But the object distance is now smaller. So instead of 1 over the object distance being essentially 0 if the object distance is big enough, that term is now significant. So in order for this to work, we need 1 over f to be bigger, or our focal length to be smaller. The light needs to bend more than it did before. So to make that happen, we actually, exaggerating that one a bit, change the focal length of the lens of our eye. Which is really cool. That's a neat ability to have. So that's why we are able to see things clearly at different distances. If you're looking at something closer, the eye adjusts to focus a little more strongly. And if you're looking at something farther away, the eye adjusts to focus less strongly. Not everyone can focus things in the back of their eye just right. So if you are farsighted, you can see things that are far away, but could not make your eye focus things strongly enough to work in this case. And if you are nearsighted, you could see things that are close, but could not adjust your lens to make it weak enough to see things which are far away. If any of you happen to be cephalopods, instead of changing the curvature, you would just move the lens back and forth and change the image distance to look at near objects and far objects. So octopi have a different technique. If you wanted to correct for nearsightedness and farsightedness, so if you had an eye like this, that's good at seeing things that are far away. I'm good at seeing things which are close. Its focusing power is too high. you can put a diverging or negative focus length lens in front of it. So it used to, and then if you have light come in parallel, it can focus into a point again. Whereas if you didn't have them, if you had the nearsighted eye without the corrective lens, lines coming in parallel, this is exaggerated how far off things would typically be. But they don't focus on the back of the eye, they focus in front of the back of the eye. So if you're looking at something that looks really, really small, its light is blurred out over a segment of the back of your eye. And a different object, which is very far away also, but at a slightly different spot, is going to blur over. So there's this spot here, which is getting light from two different objects. You can't see them as distinct things. Whereas a separate object on this one, not going to do it, would end up focusing at its own spot. For the opposite, farsightedness, you would want a converging lens, which is going to make it so that instead of got our eye, and it's going to have a low focusing power lens. So good at seeing things that are far away, but if you put a close object it would focus it behind the back of the eye, which is no good. That's not where the light is detected. So that can be corrected. By putting a converging lens in front of the eye. So then your light from that close object is too much bending from the eye. glasses. Ends up focusing. So you can just have something up the total focusing power or drop the total focusing power. And they're pretty neat devices. What astigmatism is where it doesn't focus things the same on the vertical and horizontal axis, or maybe diagonal that way and diagonal that way axis. So if you had, instead of a conventional lens, something like a cylindrical lens, so a cylindrical lens, if you look at it from one way, it bulges out. If you look at it from the other way, it's just not bulging out. So it will focus a point kind of into a line instead of a point. So that would be corrected just with the opposite kind of cylinder. So if you were measuring your eyeglasses or having an eyeglasses prescription, it would be given in diopters for just what is the strength of the lens that is correcting the focal length of your eye. Right. So I am a bit nearsighted. So the eye can adjust its focal length, but the closest object that I could see clearly is around 0.8 meters from my eye. So if I wanted to be able to see something that is very, very far away, essentially infinity object distance, what lens would I use? And you can make the not quite right assumption that the thickness of the lens and the distance between the lens and my eye are of no consequence, which is not quite true, but go for it. If you don't know where to start by finding the focal length of my eye. Right. Ah. So I'm going to make F1 my eye on its own. So 1 over the focal length of my eye on its own is going to be 1 over the image distance, 0.024 meters, plus 1 over the object distance. So the focal length of my eye on its own is 0.0233 meters. So the combined focal length is going to be 1 over our new object distance plus 1 over our image distance. So our new object distance is very, very far. Infinity-ish, so it's just 0. So combining them together, 1 over the focal length of my eye plus my eyeglasses is going to be equal to 1 over the focal length, just my eye, plus 1 over the focal length of my eyeglasses. So it's going to be minus 1¼ diopters, or a focal length of minus 0.8 meters. Questions on how these work together, combined?
I'm not understanding what is. Could you like draw a picture of what does the length of 24 millimeters? Like, what does that mean on a picture?
So I'm treating my eye as if it was doing all of its bending at a single point, which is not exactly true, but the 24
Okay.
millimeters from the front of my eye to the back. And I'm just smearing it out and pretending that the lens of my eye and the cornea of my eye and the eyeglasses, they're all at about the same spot.
Okay, that makes more sense now. I thought it
Good.
was like I thought you were talking about the height of the lens or something. So I was kind of
Oh, like going that this is 24
yeah, or yeah. But
millimeters. Being round, it's reasonably close to that, but what really matters is distances along the optical axis. This way. Worth clearing up. All right. Any ideas why seeing underwater is weird or difficult?
The index of refraction in water is different than air.
Yeah. So, and it's not that different from most of the inside of our eyes because we've got a lot of water in us. So yeah, you're used to get, in air, you get a lot of bending as it enters the eye, and in water, you get much less bending as it enters. Very good. Right, the last two steps. They're gone. The last couple steps on that one was 1 over. So the combined focal length, the inverse of that is equal to the inverse of the focal length of just the eyeball plus the inverse of the focal length of the eyeglasses, about. So to solve for F2, the focal length of the eyeglass, that's how it finished to get to the answer. Did that show you what you needed to see? Cool. No worries. So we have been using magnification to describe how big an image is in comparison to the object that formed it, as well as whether it's right side up or upside down. That is not always the parameter that really matters. Sometimes you just want to go with how big does something look? Does it seem bigger or seem smaller? Like if something gets closer to your eye, it hasn't actually gotten bigger, but it seems bigger. And the fraction of the back of your eye that it takes up will be greater. So we have lowercase m, which is just our lateral magnification or just magnification. And a different parameter, which may be what you care more about, is angular magnification or magnifying power, which, being a similar thing, conveniently or inconveniently, gets a similar letter, just capitalized. Which is, how big of an angle does this thing take up when you look at it? So if you have a magnifying glass, got our optical axis, and if you put your eye behind it, and we've got our focal points. Nope. And an object which is close to the focal point. Light from it comes in parallel, goes through the focal point, and if it just goes straight through the middle, those lines are almost parallel. So it looks like it's very, very far away. If we trace them back, maybe they'll meet way, way, way out here. For someone that is looking at it. So there's the eyeball. And we can make the eyeball much closer. So nearly parallel rays are coming in, so it seems to be very, very far away and very, very big. If the nearly parallelness changed and made it twice as far away and twice as big, to the eye, it really wouldn't look that much different. So the purpose isn't to maximize the lateral magnification, but to make something seem bigger. So this angle here is theta prime, because we can trace that out to the angular size of the object in a person's vision. If someone didn't have this magnifying glass, they can't typically hold it right in front of their eyeball, because there's a limit to how close people can focus. The closest that you can focus varies significantly person to person. Supposedly the Pelvi normal average is around 25 centimeters. So if we had our eye again, looking at something 25 centimeters away. The angle that it's going to make as it enters their eye is now smaller. So if we make it a million times, if we make the image a million times taller, yay, but it seems much farther away. What really matters is how much taller it seems to be. What is the angular height of it? So that angular magnification or the new angle over the old angle is approximately equal to, if we're willing to make our reasonable small angle approximation, the height of the original object over the focal length of our magnifying glass. So height over the focal length is a pretty good approximation for that angle. And height over 25 centimeters is a pretty good approximation for this angle. So it works out to be 25 centimeters over the focal length of the magnifying glass. Or if you don't want to assume the average eye, where n is your near point. Or the closest distance to your eye that you can clearly focus on something. This is assuming that for this setup, the eye is looking at this object, which seems to be very, very, very far away. If we change the geometry a bit, so it's looking for something that's now at its near point, so this is eye. If you strain the eye and try and look at something close, you actually can get a bigger angle. So if you're trying to focus at the near point and you're using a magnifying glass, you get an extra 1 to the angular magnification. And you can use a lens like this to make something appear enlarged. A single lens doesn't give, practically speaking, nearly the ability to magnify as a microscope, some sort of multi-lens system, but you can, double or triple how big things seem to be. All right. Last thing for today is, what if we don't want to take the focal length of a lens as a given? It should be calculable. If we apply the idea from the focal length of light coming through a single curved surface from a few weeks ago now, and did that to the front surface and to the back surface, you would be able to get a focusing power from both of those, add those focusing powers together, and get the focusing power from the entire lens. So that is the lens maker's equation. And it is this. So this is rather similar to what we got from light going through a single curved surface. It's related to that. Some differences are, for the lens maker's equation, we usually assume that the index of our lens is n, and the index of its surroundings is 1 for air. You'd need to massage the equation a bit if you were having something not in air or space. Air or space are close enough. And another important difference is we have 2 radius of curvatures to take into account. So the sign convention for this is that convex counts as positive. So you could have a lens like this. We've got a small radius of curvature for the back. And a large radius of curvature for the front. But both of these would count as positive. A double concave lens, both of these radius of curvatures would count as negative. And a lens like this, the front is concave and the back is convex. So you would have a positive and a negative radius of curvature to plug in. So this is the lens maker's equation. Because if you were trying to make a lens with a given focal length, it's the equation that you would want to use. It's not immediately obvious, or even close to that, that these are exactly what the terms should be. but big picture, I think all of the terms in here make sense. If you had an index of refraction of your lens, which is very, very close to 1, it would do very, very little bending because it's the changing of index that gives the bending. Look to Snell's law. If we have a transition, if you have an index close to air, you get just a little bending. And if you have an index which is very far from air, you can get a lot of bending. So greater difference in index gives more bending. And the smaller the radius of curvature, the steeper the angles it's going to hit, and the more tightly it can focus it. So you can get a focal length which is shorter or more bending. Let's try and use it. So lens, like this, where this larger circle, we continued it around the center of that big circle there, and continuing the front surface around. A smaller radius, somewhere like there. Not to scale. See if you can calculate it. So just using our equation for lens making. No, -8, -1. So we've got 1 over 0.3. And the back one is concave. So it's going to count as negative. So our focal length will just be the inverse of this. And it is equal to 0.9375 meters. So because the concave surface had a greater radius of curvature or a more shallow curve than the convex surface, it still is a converging lens. Questions
For
on
choosing which one to put as R1 and which one as R2, did you choose front and back as the cues for that?
I did. And if you did it the other way around, you'd be fine as long as you stuck with the convention of convex positive, concave negative. So if you had a lens that looked like this and used R1 and R2 oppositely, you'd still get the same answer so long as the concave one you still counted as negative and the convex one you counted as positive. But yes, that is what I did. I called front R1 and back R2, which I did it, but it doesn't really matter. Good question. Anything else on this one? Right. That can be a stopping point. Next time, we're going to get into optical devices with more than one lens, including the telescope. Maybe the microscope too, focus on the telescope. And get a start on wave properties of light. So how light doesn't just follow ray optics, interference is a thing that matters for light. All right, that's it for today. Any last questions before we are done? All right,
Thanks, Professor. We'll see you again on Wednesday.
see you on Wednesday.
Thank you, Professor.